just overlap space. Our admin, she's not well, that's why she's not doing.
Hello everyone, good afternoon. My name's Chris Davis, I'm the Interim Director of the Leeds Institute for Fluid Dynamics, and it's my pleasure to welcome you to our annual LIFD John Fox lecture. We've got 3 exciting talks for you. We've got 2 and then a little break, and at the break there's a number of posters and refreshments, so please do try and look at the posters while you're refreshing yourselves. Just to keep a couple of housekeeping sort of announcements. We are not expecting a fire alarm, so if there is a fire alarm, it's presumed to be a real fire alarm. The bathrooms, some of you have navigated to them. They're all the way out at the end and then right. Okay. So I'm going to keep this brief because I want to get on to the talks, but just a few words about the Leeds Institute for Fluid Dynamics. So it was established in 2018. It's a cross-faculty institute here at the University of Leeds. It spans 4 faculties and 12 schools, and it sort of oversees a really wide range of research into fluid dynamics, sort of from the very fundamental to the very applied, from biological fluid dynamics all the way up to sort of the fluid dynamics of plasmas, the fluid dynamics of liquid iron in planetary cores. So it really has a sort of, there's a vast range of sort of like research and teaching that is going on within LIFD. And I just wanted to, to point out that there are a number of ways that people can interact with LIFD. If you go on our website, you'll see that there's funding for seed corn projects, for mobility funds. So, you should go and check these things out. I also just want to say that this event is generously sponsored by Leeds alumni Arvi Ahalan, and we are extremely grateful for this continued support, which makes this lecture possible. So without further ado, I'd just like to move on to our first talk, which is going to be given by Mazen Babay, who is a lecturer here in the University of Leeds in automotive engineering, and he's going to tell us about the fluid dynamics of battery thermal management.
Thank you so much, Chris. Good afternoon, everybody. Thanks for having me. So my talk is going to be about battery thermal management. This is the area that I've been working for last few years, and I will try to actually give an overview of what's going on in this area. So basically, as you may know, transport is one of the major actually source of greenhouse gas emission in the UK. And if we want to break it to different sectors, so it would be car and taxis, the most important one, the highest share, HGV, and then light van, and shipping and others come next. And part of the emission, GHG emission is not only domestic, there is related to the emission that we are importing, which is categorized as international. In that case, aviation is the biggest one, 22%, and shipping is about 4%. So there are some targets to achieve net zero by 2050. And as you know, there is a kind of deadline for end sale of new petrol and diesel by 2030, with all new cars being zero emission by 2035. And it will then extend it to phase out of heavy goods vehicle as well by 2040, and there is a plan to removing all diesel, only train by 2040 from UK road. So, based on this introduction, basically battery are expected to play a major role, and the good news is actually their price is dropping quite significantly. So since 2010, the price dropped over 90%, and currently it's just over $100 per kilowatt hour. And the prediction, the expectation is to get to about $80 per kilowatt hour by 2030. So they are getting cheaper. They are getting better in terms of energy density and performance. There is some recent statistic out that's showing like the real data of EVs. They still kept over 90% of their capacity after 150,000 miles. So they are all good news, and as you can see, new chemistries are coming. So the energy density of lithium ion is around like 200 watts hour per kilogram, but actually it's expected to increase with new chemistry to 300 to 500, with like having the basically solid state coming to the market, and like there is some research exceeding the energy density to 500 watt per hour per kilogram by actually some new development in this area. How the battery system is working, so everything will start from cell. So lithium batteries are designed flexible. They can be formed into a wide variety of shape and sizes to efficiently fit the available space. So we start from the cell, making to the module, and then module put together to actually make a pack. It needs to deliver the voltage, amp, and energy required by your driving system. In that actually process, when we're getting from the module to the pack, we're getting like more component. We are losing a bit of energy density when we are packing. About 25% to 40% of the energy density is lost. That's why even in this process, the design itself is quite important, which actually the thermal management will play a significant part. Looking at the topic of today, which is basically the lithium-ion battery. So batteries are quite sensitive to the temperature. And you know, as you can see here, they depend vastly on temperature for facilitating an optimum performance and lifetime, with commonly suggested the operating temperature to be between 15 to 35 or 40 degrees. As you can see in this picture, operating at basically lower or higher temperature than the range can have a negative effect. It can lead to lithium ion plating or electrolyte decomposition at low actually operation. And if we go quite higher, again, we will have the problem of like increase in the resistance, and even gradually, if the temperature increase a lot, we might get to the thermal runaway actually performance. Apart from the temperature, like the absolute value of the temperature of the cell-to-cell variation temperature is quite important. So we want to keep it like less than 5 degrees to make sure that, first of all, it's operating safe, and we are basically aging kind of uniformly in our battery pack or in our battery system. Looking at the mechanism that heat is produced, so heat in a battery is produced by through actually two mechanisms. So entropy change, delta S, from electrochemical reaction, which can be either positive or negative, and Joule share, which is heating generated when electric current is transported across a resistance that we call it actually ohmic heating, which comes from the ohmic resistance. At low discharge current, heat generation is mainly dominant by entropic effect, versus Joule heating become dominant at very high C rate. In the discharge process, the battery experiencing an exothermic chemical reaction, while during the charging process, the battery experiences an endothermic, basically, chemical reaction. However, as the heat generated from Joule heating is relatively larger than that of the endothermic reaction during the charging as well, the battery cell can still actually generate heat, and we will see the increase in the temperature. It's very dependent on the SOC state of the charge of the battery and the power or C rate that we are charging our battery. Also, thermal runaway is another actually parameter that is quite important. So if the basically electrochemical breakdown of the anode began to happen around 85 degrees of actually Celsius, so we need to make sure that we're keeping temperature below that. There are some actually triggers for that. It could be mechanical trigger, as you can see. It could be thermal trigger if there is not a good actually cooling system in operation, or there is a fault in the system, or it could be basically electrical problem that may lead to the thermal runaway as well. So I think now it takes us to the battery thermal management, which play a critical role to keep actually the battery in the temperature that we want. A BMS, a battery thermal management, is not just the cooling system itself. In general, it includes like components such as cooling system, heat sink, heat exchanger, fan, pumps, temperature sensor, expansion tank, and control valves. And all this together will manage and keeping the temperature of the battery in the range that is acceptable. So BTMS heating transfer, there are basically, we can categorize it in two major actually categories. The first one is direct contact, which actually the fluid is in direct contact with the batteries. Is more for the older actually design, older vehicle where the battery was small, the actually charging and discharging demand was small. But many modern vehicles these days are using basically indirect cooling, which has got like different shape. It could be plate cooling or from the side or from the tap. It has got different design depending on the application. There are some factors that affecting actually performance of direct or actually indirect by having the pipe medium. So battery pack geometry, the space between battery and battery layout configuration will significantly affect the performance of the basically battery thermal management system. On the other hand, when we have a medium for the heat transfer, so the contact area is quite important, the dimension of the pipe, height, thickness also playing a role. And there are some actually fluid mechanic criteria that is important in both of them. Basically, the type of coolant that we are using, the velocity, and the environmental temperature will have a kind of significant effect on the performance of our thermal management system. So for the actually coolant like material or the typical coolant type for the battery management system, air-cooled was probably very common. Started like majority of the system started with air-cooled because it was very cost-effective due to the simple design, but also the low heat capacity of air will limit actually the heat transfer. And as I said, the majority of the vehicle these days will go to the liquid cooling because of the high heat capacity of the liquid. And efficient heat transfer, but complex design and construction that we have. And also, there might be an issue of leakage. Quite recently, PCM material started to actually penetrate, and there are a lot of work mainly on the basically kind of research phase on looking at the phase change material. But I personally haven't seen any industry that using it or adopting it in a kind of operational scale. Yet. There are some actually new technology also coming to the market. Immersion cooling is one of the major one, which actually some of the traditional oil companies such as BP and Shell has got interest on that. It's like specifically interesting for high performance vehicle, which you are dealing with high C rate, and also some like large applications such as ship, that you need to carry a lot of actually battery and a lot of heat should be transferred. The other actually emerging technology are kind of hybrid cooling, so combination of liquid with the air cooled is quite actually emerging, as well as like we are seeing a lot of design with the heat pipe and a combination of PCM with other technology, including the heat pipe. So here, actually, there was a kind of a study done in 2022, and it just looked at the kind of comprehensive, basically, type of battery thermal management to see how they are operating, how they can keep the temperature between 25 to 40, and the cell-to-cell variation between 0 to 5. And as you can see, they can get to kind of some design, almost, all type of this design, depending on the application, can deliver this one, but if we go from one application to another, it's not necessarily would be the case. So with this actually overview of BTMS role, the current challenges of BTMS actually that is open and we are in the research. As I said, uniform temperature is a problem. It's hard to get like the cell-to-cell kind of gradient of between 3 to 5 degrees. That's one of the basically driving force for immersion cooling technology that can keep the cell temperature quite uniform. Fast charging is another big challenge these days. So we are talking about like probably 5C, 10C or above charging, which is quite significant amount of power, and it will produce a significant amount of actually heat. So the fast charging itself is quite challenging. That's another challenge for the battery, the thermal management design. When we get to the more complex system, the energy actual consumption of the battery thermal management system itself is a challenge. We need to think about that. And one of the kind of major risks these days is about looking at the thermal runaway, and more specifically thermal runaway propagation with the newest standards coming that require to keep the thermal runaway within the module or pack for a certain amount of time and actually avoid kind of propagation to give enough time for the reaction. And like the last but not least, so the cost constraint and the packaging space plus weight is another actually major challenge for battery thermal management. So what we are doing at Leeds and many other researchers are doing, we're using model to address some of these challenges. We start the modeling from cell. So there are, like this slide is showing like the kind of major model that are available and in use. The very kind of most common one is ECM, equivalent circuit model, which actually quite simple, and it represents the battery with a couple of resistance and capacitance, and we model the battery in this way, which actually, as you can see, later on we can get the Q by just simply multiplying the resistance by I squared. DFN, which also called P2D, is probably the best model in terms of like representing the reality, but it has got a lot of actually parameter involved. It needs cell tear down, and it's quite complex. But when we are dealing with complex problems such as thermal runaway problem, probably that would be the best option. The simplified version of actually DFN, single particle model with electrolyte, SPME, and one stage further, single particle model SPM are two kind of simplified model of the P2D that is also commonly in use. And NTGK is like the model that ANSYS is using, and quite famously many of actually battery thermal management design is done based on that. Quite recently, reduced order model started to penetrate because we are looking at kind of faster simulation, reducing the computational burden and allow real-time estimation of temperature, especially when we want to relate it to the BMS design. So battery thermal management and control, they are required a kind of fast model. So reduced order model started to penetrate. So there are a couple of actually major reduced order model that is developed these days. So POD is one of them, and as you can see, there are two others. Also, ANSYS Fluent has got his own reduced model that's actually relying on a scaling method rather than traditional projection-based reduction. In terms of software packages, so these are the list of the major software packages that are in use. ANSYS Fluent, as I said, quite common, so CFD-based, MSMD module, as you may know, and some reduced order models are in there. PyBAM, quite recently, with a kind of funded project through EU, has got a lot of actually development. The good thing about PyBAM is you can actually, it facilitates the development of physics-based model, including like P2D model, and it's quite useful. COMSOL as well, so it's using finite element method for electrochemical thermal coupling. It's especially quite useful when you want to look at like multi-physics operation. OpenFOAM and STAR CMM are also two major actually tools that we are using in battery thermal management. Okay, with this kind of overview, I just quickly go through some of the work that we did at Leeds. So the first one is about one-dimensional electrothermal model. It initiated from an Innovate UK funded project that we look at basically powertrain design for a 44-ton truck. We wanted to see how the electrification of that truck would look like. So we look at basically different driving cycle. So we define the powertrain based on the different driving cycle. We use NMC cell, NMC chemistry because of the high actually energy density, and we look at like how would be the performance in urban, regional, and long haul delivery. Also, we did all this work in a software called AVL Cruise M because of the contact we have with AVL. We also tried and model or simulation for a kind of real driving scenario that was provided by AVL. So as you can see, these are the number of battery pack that would be required based on this one. As part of this modeling, which was about powertrain, we also developed an ECM model of the battery. We just characterize a cell in the lab using a standard test called HPPC test. Based on that, we characterize a cell, and we develop an ECM model of the cell using MATLAB, actually Simulink. The good thing about this simulation is without going through too much detail, you would be able to get like a kind of general overview of the performance and application of actually your system, looking at how your thermal performance would operate, what would be the effect of actually different C rate, what would be the effect of different flow rate, and get a kind of overview without the complexity of the 3D model that exists. We also did a lot of work on 3D actually modeling. So this result is actually one of our most recent work that is published, that is submitted and is under review at the moment. So one of the actually kind of gap in literature is the powertrain design and battery thermal management are separated from each other in the literature, while in industry they are done together. So what we did, we designed the powertrain for a heavy-duty truck. We extract the real power, we translate it to the amp, and then we look at the battery performance, and based on that, we did a kind of battery thermal management design and analysis. The other novelty that we had here, we didn't look at just a steady-state operation. We also look at the basically transient analysis of the battery performance to see how the battery will perform in the transient condition. We apply the hybrid cooling, which is a combination of basically liquid plate cooling as well as the basically air cooling on this vehicle. So there are some detail that how we translated the power to actually temperature. And basically, as you can see here, so what we did, we look at like some critical actually area to develop our transient analysis to see how the battery will perform in this transient area and how our cooling system will react to make sure that it's quite safe. So if it's safe for those areas, we can conclude that for whole driving cycle, it will deliver a kind of good performance and operation for us. So these are some of the results. So we look at like different inlet velocity for air and different actually flow rate, which translated to Reynolds number. So we realized that increasing the liquid coolant inlet Reynolds number beyond 9,000. So as you can see here, for most of the graph, it's becoming like kind of flat. So there is no point to increase basically the velocity and flow rate. So it doesn't give us much benefit for the plate cooling. So we concluded that we can actually keep 9,000 as a kind of criteria. Also, we look at the inlet air coolant velocity and the pressure drop that we will get. And based on that, we concluded basically 5 meters per second would be like the kind of economical one, because increasing from 5 to 7 will correspond to about 100% increase in pressure drop in our system. So there are some actually summary of the point. The other work that we have done quite recently is on immersion cooling. So immersion cooling would have like different, can be done in different form. So pump liquid is the major one, the most common one that is used, but we can also using like two-phase as well as the spray cooling in this one. Probably in the interest of time, I just passing a few slides, just kind of introduction here. So what we did here, we look at like the high C rate, because the standard soon will require us to have between from SOC 10 to 80% in 10 minutes. It's required quite fast charging and actually producing a lot of heat. Also, extreme temperature are becoming a problematic with global warming that we are seeing. So we look at like quite high temperature variation in this analysis with quite high C rate. So again, we actually started with the cell actually simulation, and then we went to the kind of immersion cooling, so some validation. I probably jump and go to some of the results that we found. So at like this data here, so the temperature at the top basically showing the environmental temperature, and here is showing like the inlet velocity of our fluid. So as you can see, we're trying to keep the temperature below 308. So to have that's actually keeping in the safe or the advisable range of the operating condition. So we try to see at each environmental temperature basically how much flow rate would be and how the system would operate. So depending on the environmental temperature, when we are dealing with about like 30 degrees, so it's quite achievable with like quite a reasonable range. We can reduce the temperature, but when we go higher and higher, so it's becoming more challenging, and we would need to have like increasing the flow rate quite significantly in our system. What we also did kind of add to that, we also look at the kind of effect of the nanofluid. We use CuO and alumina as two kind of nanofluid to see what would be the performance of them. Here we use MSMD module of ANSYS fluent, and we realized that with a small actually amount of nanofluid, about 5%, we can achieve a temperature reduction of about like 5 to 7%, depending on the type of nanofluid that we are using. However, the pressure drop should be considered when we are actually applying nanofluid. So that was actually the analysis we also did for pressure drop. At low velocity for like 0.5% and 2% concentration, the pressure drop was not quite significant, about 1 to 5%, but when we increase to actually 5%, the pressure drop is changing between 8 to 12%, which becoming quite significant as well. The other work that's actually published, I think 2 years ago in Energy Storage Journal, we look at a kind of improved design of the battery thermal management. We use some basically orifice here. So we use some orifice here to actually complement the battery thermal management when needed. So it was originally an air-cooled battery thermal management, and we tried to actually inject highest speed air as well as liquid when needed at high C rate to make sure that to improve basically the performance of our battery thermal management. Again, here we use MSMD module of actually MATLAB, and the good thing is, as you can see in this picture, so we could achieve, and the data is showing here as well. This is the kind of length of the basically battery. So we look at the temperature variation across the length, by using this technique, we could achieve a kind of not only a good cell-to-cell variation difference, but also the temperature variation across the cell was actually improved, and we could actually reduce the temperature variation across the cell as well. So we are also quite actively involved in Horizon project. This was the project that we submitted last year, looking at the light weighting of basically battery thermal management system with the involvement of like some major player. Porsche was there, Proventia, Toshiba, and others. So unfortunately, we get to the reserve list. We are waiting to see if extra funding is available. We also look at like the electrification of ship quite recently. That was again another proposal, a Horizon proposal. This one again in recent, like reserve list quite recently, but it was kind of a decent size. So we wanted to demonstrate 40% increase in fully electric long distance autonomy for maritime vessel about 400 gross tonnage. And in this one, we use immersion cooling, and our role was on the design of basically the battery thermal management. This is the one that we submitted recently. Also, Harvey is involved. We are just a few weeks ago, we are going to look at accelerated multiphysical and virtual testing for battery, aging, reliability, and safety evaluation. Again, the testing time is matter. If we can reduce the testing, reduce some of the tests with the model, it would have a quite significant in time to market and bringing like making the Europe cell manufacturer and battery manufacturer more actually competitive. So thank you so much. Sorry for going a bit slightly over the time.
Thank you very much for a very nice talk. Can I ask for a couple of questions? Yeah.
That is loud. I just noticed on one of the slides you said something about having 2 hours between the start of the battery going into thermal runaway and it catching fire, exploding. That seems like quite a long time. I mean, from my experience, I've maybe mostly heard descriptions and videos of like the actual event of it catching fire. It happens very quickly. So how would they determine when a battery is starting to go into thermal runaway, and how would you slow that down and cause it to last that amount of time?
Yeah, I think you are referring to this one. Yeah. This is actually quite recently came to the market. So record that EV battery don't catch fire or explode for at least 2 hours after a thermal runaway. Yeah. So basically, they using some actually kind of technology in the, for example, in the other project, the Weisbad that we had, there was a American company. They developed some material that somehow expand and just isolate the cell that is going onto the thermal runaway to make sure that that is isolated and it doesn't actually kind of let the thermal runaway propagate to others. I think the other thing we need to know is the thermal runaway is the kind of result of a chain of the phenomena. So it's like 80 degrees is just a start, and after that it would be self-contained, and I think with the rate of 2 degrees per minute, it will start to go like increase to going to the what we see as an explosion and thermal runaway. What they also trying to do is somehow capture that's 80 or before when the chance of thermal runaway is high. Try to bring some actually measure into the place and also even stop the operation or make sure that the battery doesn't go fully in the thermal runaway.
Okay, can we thank Mason again, please? Okay, so to continue our theme of fluid dynamics and net zero, it's my pleasure to welcome Professor Fleur Loveridge. Fleur is a professor of geoenergy engineering here at Leeds, and she's going to talk about net zero warm buildings.
Hi, and thank you very much. We're going to change tack a little bit now and talk about flows that happen beneath the ground, and hopefully this will be a nice kind of entree to our keynote speaker after the break. So I'm going to give a little bit of a background to why we're interested in this challenge, a bit of a comparison between heat flow and groundwater flow, which are the two sort of flows we need to analyse, have a bit of a tour of different sorts of ground heat exchangers, the ways we can use the subsurface to extract thermal energy or store thermal energy. I'll say a bit about campus geothermal here in Leeds because I think that's the topic people here will be interested in, and along the way pick up some themes of heterogeneity which I think we will come back to again later this evening. So the problem we are dealing with is something that I think is very much still an elephant in a room, and that's the decarbonisation of heating. So we've done a really amazing job in this country of more than halving the carbon intensity of our electricity grid, but still about a quarter of our emissions relate to heating and cooling buildings. And it's not a terribly sexy topic, but it's quite an important one. The grid transformation has happened without people noticing. You can still plug in your phone charger, get some electrons, power your batteries up. But to change your heating system to be net zero, someone's probably got to come into your house, come into this building. So we need to think quite carefully about it, and we still have a lot of work to do. I want to put that challenge in the context of the electricity grid as well. This chart shows energy consumption in the UK in a seasonal pattern. The red line is electricity consumption, and the blue lines are related to gas consumption, and gas is what we typically use for heating. And the main point I want to make here is that when we're using gas for heating, it can potentially, depending on the measures we use, be between 3 and 5 times the amount of electricity usage in winter when we have peak heating at this time of year. So if we decarbonise by electrifying, hopefully not by direct electric heating, because that's not very efficient, hopefully with heat pumps or with district heating, we're still going to be putting a big extra demand on the grid, and we need extra infrastructure for that. As a result, the efficiency of our decarbonisation in energy terms is really, really important. And that's why heat pumps and the ground are an important tool, because the ground offers us an energy source, a thermal energy source of higher temperature than the air, which is the alternative with heat pumps, where we can potentially achieve efficiencies of 3 or 4, which makes a big difference on the electricity infrastructure we need to build. So how can we use the ground to source heat to decarbonise our buildings? We have a number of different options, getting deeper and hotter from left to right on this slide. We have shallow, what I'm going to call a closed loop system, where we circulate a fluid through usually plastic pipes embedded in the ground, typically in boreholes, maybe in horizontal trenches, and that allows us to bring heat to the surface to put into a heat pump system, often connected to an individual building. Next along, we have a relatively shallow, what I'm going to call an open loop system, where instead of circulating water in a closed loop, we're actually taking the naturally occurring groundwater out of the ground and putting it through a heat exchanger and a heat pump, and that might be for an individual building or it might be into a heat network. We've also, in places like Leeds, have opportunity to use old flooded coal mines, which might be a bit deeper and a bit warmer, and depending on the depths of the different rocks, which might be able to supply water, we might be able to get hotter water at greater depths, and that is something that they are aiming to do just down the road from us at the University of York. So in order to analyse how we can bring that heat to the surface and use it in our decarbonisation, I just want to briefly touch on the fundamental physics that we are analysing, which hopefully for a lot of people in this audience will be telling people how to suck eggs. However, I want to draw attention to a couple of things. The first is the analogy between heat flow and groundwater flow. So heat isn't a fluid, but we're often analysing it in CFD software because the processes and the maths behind it are directly analogous. If we look at Fourier's law and Darcy's law, that is very obvious indeed. One, we have a proportionality constant of thermal conductivity. The other, I am going to use hydraulic conductivity K, because I'm a geotechnical engineer. I'm not going to get into permeability. And I'm also expressing Darcy's law in terms of change in head, because I'm a geotechnical engineer, because I'm dealing with water as my fluid in the things that we are talking about. The other thing I wanted to point out in the context of groundwater flow and Darcy's law is that we have a volumetric flux per unit area, which is effectively a velocity, and I will be talking about Darcy velocity quite a bit. And I just want to remind people that this is not the true speed at which the water is moving, because the water may be taking a much more convoluted path, either because it's in a porous media or a fractured media, as per the sketches on the right. We might be dealing with a three-dimensional problem, but a lot of problems in ground heat exchange for heat pump systems are simplified to one-dimensional radial transient flow. So I'm going to be referring a few times to the infinite line source. If there are any hydrogeologists in the room, that is a perfect analogy for the Theiss equation, which is used to interpret groundwater pumping tests. It's basically radial flow into a well, and we will come back to that one again as well. Obviously, on many occasions, both these processes are happening simultaneously and are coupled. So a lot of the time, we're going to be solving the advection diffusion equation in this talk. There are other processes happening as well outside of these equations that I will come back to, but mainly the analysis I show would be based on these. There's one more equation I want to put up, and that's for the thermal power that is available from the ground, which is a function of the mass flow rate of which we can extract water, either from our closed loop or our open loop, the specific heat capacity of that fluid, and the temperature difference between our source and our sink. And the reason I want to draw attention to that is because that controls how much energy we can take out, if you additionally take into account the time scale that you're taking it out of. And because of this, those open and closed loop solutions to taking thermal energy from the ground have different characteristics. So if you have an open loop where you're pumping water from the well, you can have much higher volumes of fluid flow and much higher rates of heat transfer. But you can't do it everywhere. You need an aquifer that has readily available water. It also has slightly higher risks because you need to drill a well and check that you can get those pumped flow rates to deliver the energy you think you can. Closed loop, by comparison, you have much lower energy, much lower power per well that you drill, but you can do it absolutely anywhere. It's not dependent on the ground conditions, and it's very low risk. You know it is going to work. Now, at the moment, in this country, we're a long way behind our heating decarbonisation challenge. We take about 1.4 terawatt hours per year of thermal energy from the ground, which is less than 0.5% of our demand nationally for heating. By comparison, our calculations for the city of Leeds show that from open loop systems, we could be taking 60 terawatt hours per year alone, just in this city. So the point I want to make here is that the scale of the resource is absolutely huge. Now, often we don't do things like this because it's expensive, but my argument is, where else are you going to get this scale of resource from to tackle the challenge that we have at the high efficiencies that we need? So I'm going to talk a little bit about closed loop now, and then go on to open loop. So thinking about those physical processes that happens, if we have let's face the right way, a single closed-loop borehole heat exchanger, and if we just have diffusion or conduction happening in the ground, we will get some temperature contours like this if we extract or inject heat. If we additionally have groundwater advection, possibly dispersion, we will get contours like this. If we have vertical diffusion as well, we will get constraining of those contours on the top and the bottom. And those are the processes that are happening. And if we translate those into a design chart, on the right, we are plotting a non-dimensional temperature change against a non-dimensional time for a constant rate of heat extraction for a number of different conditions. So our straight blue line here is if we have an infinitely long heat exchanger where we've only got conduction happening radially, the infinite line source I mentioned earlier with the equations. If we either constrain that with vertical diffusion or we add our groundwater flow, we start having these curves roll over. And the further down here we come, the faster our Darcy velocity is, the larger our Peclet number is. So what you get when you have high groundwater flow is a situation whereby you're taking heat at a constant rate, but you're changing the temperature no more. Okay? So it means you have more energy available. So in that sense, it is advantageous. There are some disadvantages, which I will come to later. To put that in the context of a practical example, we did some work looking at the energy available from putting closed-loop ground heat exchangers in tunnel linings beneath Manchester as part of HS2 when they were going to build it there. And the chart on the right gives us some heat transfer rates based on the temperature difference between source and sink for different geological conditions. And the values at the bottom of this chart are equivalent to heating about 600 homes per kilometre of tunnel lining turned into a heat exchanger, and they would be applicable to mudstones without any groundwater flow. Things in the middle might be applicable to sandstones with groundwater flow, but because we're here talking about fluid dynamics, I want to draw your attention to the red circles at the top. They are where you have high airflow in the tunnel. And here you get a win-win scenario where you reduce your need for tunnel ventilation to cool as the high-speed trains pass through, and you can take that heat out and use it to potentially heat thousands of homes above your kilometre section of tunnel. So the power of groundwater and the power of air movement in your tunnel are significant. The next example I want to talk about is about the reality of ground conditions. So that example I just showed you was assuming very much idealized porous media Darcy flow conditions, which is easy to analyze. These are some results taken from injecting heat into a closed loop borehole heat exchanger in an open borehole in the chalk aquifer in a field in the south of England. And whilst we injected that heat, we equipped our heat exchanger with distributed fibre optic temperature sensors to allow us to see how the temperature changed down the hole. So when we were here, we were looking at beautiful radial symmetrical patterns. What we see on this chart on the right is the colours give us the temperature. This is time, this is depth down the hole. Previous testing tells us we have groundwater flow in these blue horizons. And here you see lower temperature change when we inject heat. And above that we see higher. And here we see higher. And you can see very high variability at high spatial resolution in between as well. So we have a real pattern of heterogeneity revealed by detailed sensing. And we can use a version of the infinite line source, which is a solution to the advection diffusion equations, assuming our line heat source is moving along, to convert that data into effective Darcy velocities to analyze what is happening with the groundwater. And we can see quite high groundwater velocities, so these are equivalent to the lowest level on the design charts I showed a couple of slides ago. Severe heterogeneity, and we know from other data from this site that the flow is fracture dominant. So maybe don't take these as real Darcy velocities, but it's an indication of the heterogeneity and the role of true ground conditions in making things not quite as simple as we think. So moving on to open loop systems, and I'm going to use the case study here on campus to tell you a little bit about that. So, these blue lines indicate the district heating network on campus to bring hot water or steam to our buildings. I work up here in engineering. What we are planning to do is take the yellow part off the steam system, which is generated by burning fossil fuels, and put it onto a hybrid ground source, air source heat pump system. And in the year before last, we drilled a series of boreholes around campus to allow us to get information to design that system and to also provide a pair of open loop wells. So the open loop wells are here at either end of Henry Price. We also have some closed loop wells, one behind engineering, one near the residences down here, near Priestley, one near the business school, one near Henry Price, and we also have a couple of pilot wells where we cored rock. And that's all going to feed into a complicated engineering system. I thought I'd show this because I thought there might be some engineers in the room. Right. So here are our wells. Here are all the engineering buildings and the Henry Price that are going to come off the steam system. The wells are going to be connected to a series of air source heat pumps and ground source heat pumps to deliver heating at 80 degrees to those buildings. That will allow them to be taken off the generating complex. Everything else on campus is still going to be on that. We're taking electricity from incoming substations. I'll just say a little bit now about the groundwater and thermal conditions associated with that. So here are our two open loop wells. They pass through this kind of yellowy aquifer called the Ellen Flags. We have some deeper holes that also go into another aquifer down here. Pumping tests done in those open loop wells showed very high flow rates, up to 29 litres per second with relatively small drawdown and high transmissivities. If you convert those into a field scale hydraulic conductivity, it's about 1 × 10 to the minus 4 meters per second, which is very significant, much more significant than expected. And last week we got some data from element scale testing for porosity and permeability, which, if I've correctly converted it from Darcy's, gives nothing more than about 1 × 10 to the minus 8. So the individual bits of rock matrix are really, really low permeability, and all the flow is happening through the fractures. In terms of our thermal characterization, we did some thermal response tests, which is like a pumping test, but you're injecting heat. We had 2 contractors interpret those, which is on the left side of this table, which is why we've got 2 different sets of values. It includes some really high thermal conductivities, which we know are not correct, up to around 10 watts per meter Kelvin. We also did some lab testing on the individual pieces of rock, which show both anisotropy and variability across the different geological units, and with much lower values. We think it's more like 3.5 watts per meter Kelvin on average. That has allowed us to do another back analysis for the groundwater, and we think we might have about 0.5 meter per day here as well, which again is a very significant value. We can then take all that information about the characterization of the ground and apply that to see what would happen if we operate our open loop system. So this is some, again, classical solution of the advection diffusion equations. It's not explicitly capturing fracture flow. For a couple of groundwater scenarios for the campus, we've taken the known heating demand of the buildings and used that to change the heat demand inputs to the model, run it for 25 years. We have a uniform set of properties for our aquifer with no flow in the strata above and below. In the high groundwater scenario on the left, here is where we're taking out water at 12 degrees. We are developing a cool plume going downstream. Here, when we have lesser groundwater flow, we still have a cool plume going downstream, but this is our second well, and because conduction is more important relative to convection, we're potentially moving towards thermal breakthrough to that well in 25 years. So there's a couple of points that come out of that. Having high groundwater flow helps us provide a high heat demand. It reduces our risk of thermal breakthrough between our wells, but it creates a downstream cool plume. And is that a problem for our neighbours or the environment, and should we care about that? Arguably, there is work to do on how this whole situation is regulated. In the UK, we do have to apply for permission from the Environment Agency to do this and supply information, but it's still very much a developing regulatory and governance arena. High groundwater flow also means it's harder to develop storage, which is something that's important to load shift the peaks of demand. So a couple of kind of takeaways from that. The flow and the flow direction are really important, but we don't normally measure it. Typical engineering site investigation doesn't measure these things. And finally, I just wanted to draw attention again to the fact that although the analysis I've shown is relatively simple, we know the reality is much more complicated than that. These are some of the rocks from the cored wells beneath the site. You can see, without being a geologist, that there are different materials there. You can see, without being a geologist, that there are fractures there and that these will have an influence on the flow conditions. There are other things I've not really talked about which will affect what happens with the heat and groundwater coupled processes, one of which is how much the fluid interacts with the rock matrix as it passes through the fractures, and I think Matt will say some more about that subsequently. There are also potentially other coupled processes, chemical reactions, thermomechanical processes happening in these materials. We're talking here about beneath the groundwater. If we're talking about shallow closed-loop systems above the groundwater table, you may also get phase change between the seasons. So it's an interesting problem to be thinking about. So to wrap that up, heating's still a big challenge, but the answer to the problem is potentially beneath our feet. The resources are huge. We should be tapping into it more. If we're going to work out how much energy we have, what the environmental impact of accessing it is, and how we govern that process, we need to understand these coupled processes of heat and water flow in the subsurface, and that includes getting a handle on the heterogeneity, including the anisotropy. What scale we measure those things at is important, and at the moment there's very little guidance for what we should be measuring and how we should be measuring it. We need then to feed that into appropriate levels of detail in engineering models, right? It's important that academics understand everything, but there has to be something we can adopt routinely to make assessments that captures the most importance of these processes. So that's it from me. As ever, anything I talk about is usually done by lots of other people. This is a non-exhausted list of the leads people involved in the things I've talked about, with thanks also to the Imperial and BGS teams who have collaborated on the site in the Chalk, in the south, and HS2 team as well. Thank you.
Thank you very much for a very nice talk. Can I take some questions?
Hi, very good talk. And I'm actually interested in understanding how the costs compare and whether you have any advice for us, because sometimes net zero obviously is a highly political discussion. Costs are highly political discussions. So it'll be nice to see how all of this work plays towards decreasing costs for the consumer in the end.
Okay, so there are a number of different issues about costs. So costs between open loop and closed loop. The initial cost related to open loop might be less for drilling because you're drilling fewer holes, but there are more risks attached to it, and there is a longer regulatory process that also costs money, so it depends what you're interested in. Costs compared to other solutions, this is where I think there's an absence of a policy piece, right? So if you think about yourself as a domestic home owner, you probably want to think about your capital costs. They're quite important to you. So you're unlikely to install a ground source heat pump system because it will cost a lot more money. It will cost less to run, but the payback period for you personally to get your money back might be longer than you like. However, if you think about us as a nation and the fact that if everybody directly electrifies their heating with an efficiency of 1 instead of an efficiency of 3 or 4, the cost of the national cost to the electricity grid infrastructure that we would need to provide to allow that is huge, possibly unaffordable. So there needs to be a better system in place to incentivize decisions to be made at a local level that will serve a national agenda to enable the transition. Because ultimately, if we don't make the transition, the costs of not doing so, have been shown many, many times to be more than the costs of doing so, like thinking back to the Stern Review and things like that. So it's something we have to do, and there is a lack of joined-upness between local and national policy making in different government departments at the moment.
I think we have this terminology of levelized cost of electricity or energy that tries to capture this capital cost and the operating costs and over a long period. Is there a number that I can go away with for this in comparison to, say, heating?
So not off the top of my head, but what I'm going to do is direct you to the British Geological Survey's geothermal platform, which came out last year, where you can go and get that information for every part of the country for the different options of the technology, depending on the ground conditions.
Peter.
This is very local. I noticed on your campus map you had a data centre in the north part of the campus.
Yes.
Is the thought there that we could add to the heat by taking excess heat from there? Is there any way we could actually use the heat to generate power to contribute to that, or is that
not to generate power, because it won't be high enough temperature, but it is very much in the discussions between ourselves and the net zero team and the estates to keep on the table the option to take waste heat from the high performance computing in Scape to be able to put it in the ground to increase temperatures, to increase efficiency and reduce our operating costs.
Thanks.
Okay, we have a short break to rehydrate our brains. So can we please just thank Fleur again, please? And our keynote talk will begin at 6 o'clock.
thought that she was real slick. Then she ran into Alfonso Brown. She hasn't been the same since Alfonso put her down. Sister Sadie never worried. Sister Sadie never hurried. Then she ran into Alfonso Brown. She hasn't been the same since Alfonso put her down. She just paces round the floor. She don't have no mind no more. She just stares into an empty space with a frown on her face. Sister Sadie was a honey, always had a lot of money. Then she ran into Alfonso Brown. She hasn't been the same since Alfonso put her down.
Still
that she was real slick. Then she ran into Alfonso Brown. She hasn't been the same since Alfonso put her down. Sister Sadie never worried. Sister Sadie never hurried. Then she ran into Alfonso Brown. She hasn't been the same since Alfonso put her down. She just paces round the floor. She don't have no mind no more. She just stares into an empty space with a frown on her face. Sister Sadie was a honey, always had a lot of money. Then she ran into Alfonso Brown. She hasn't been the same since Alfonso put her down. thought that she was real slick. Then she ran into Alfonso Brown. She hasn't been the same since Alfonso put her down. Sister Sadie never worried. Sister Sadie never hurried. Then she ran into Alfonso Brown. She hasn't been the same since Alfonso put her down. She just paces round the floor. She don't have no mind no more. She just stares into an empty space with a frown on her face. Sister Sadie was a honey, always had a lot of money. Then she ran into Alfonso Brown. She hasn't been the same since Alfonso put her down.
That's very kind. That's very kind. I just didn't want to get up and wander around. I know what you mean.
Okay, welcome back, everyone. So it's time for the main event. To finish off our fluids and net zero theme, it's my great pleasure to introduce Professor Matt Jackson, who is Professor in Geological Fluid Mechanics at Imperial College London. Matt's research involves understanding fluid flow behaviour in heterogeneous geophysical porous media, which he looks at by combining experiments and modelling approaches. And this research has a wide range of applications, including volcanic magma processes, CO2 storage, and novel mineral extraction methods. And Matt's work has been widely recognised, including winning the 2022 Alfred Wegener Award of the EAGE for outstanding contributions to the ongoing transition to a low-carbon energy future. So without further ado, I will hand over to Matt for his talk on geological fluid mechanics in the energy transition.
Great, thank you very much, Chris. Good evening, everyone. It's a real pleasure to be here. I hope you are continuing to explore the fluid dynamics of wine and beer during my presentation. I will talk a bit about geological fluid mechanics in the energy transition, and I feel essentially this is really about sort of flow in porous and fractured rocks, so it builds on some of the work that, or what you heard from Fleur, and in fact it has a very wide range of applications that are relevant to the energy transition. And this is very challenging fluid dynamics, okay? We're looking at a couple processes of flow and heat transport, but also chemical transport, the potential for chemical reaction between the fluids and the rocks, multiple scales spanning the pore scale up to the scale of tens of kilometers in the crust, length scales varying from seconds up to in fact millions of years, as you'll see in some of my presentations. And that means it's a really rich area to work in. So I do focus on geological fluid mechanics. I think it's a really rich time to be a geological fluid dynamicist or mechanicist with all of these different applications of geological fluid mechanics to the energy transition. Now, if I could keep you here till midnight, I would talk about all of these, but I can't, so I won't. So I'm just going to focus on a couple of these areas listed here. And the first is to pick up on something that Fleur talked about, which is essentially geothermal energy for heating and cooling, and also I'll emphasize the potential to use the underground for thermal energy storage. So, Fleur kind of introduced us to the challenge here. Heating of buildings in the UK accounts for around a quarter of our greenhouse gas emissions. We also need to be cognizant of the challenge of cooling as well. I know on a day like today it doesn't feel like that, but in fact we have a cooling problem as well in the UK, and there were lots of newspaper reports over the summer of people living in uncomfortably hot and unhealthily hot buildings in the summer. So we need to look at both heating and cooling as a challenge for us, for us here. And it's a difficult sector to abate. As Fleur said, we need local, place-based solutions to deliver low-carbon heating and cooling. We can't just switch to electricity. Heat pumps are the solution because they offer a more efficient solution, and we can ground source those or we can air source those, and I will be focusing, of course, on ground source. But I shall make some comparisons against air source heat pumps as we go through. So Fleur nicely introduced us to some of these shallow geothermal technologies that can provide low carbon heating and cooling, and she pointed out the difference between closed loop systems and open loop systems. I'm going to focus today on open loop systems because I'm really interested in how groundwater flows in the subsurface and how heat is transported in the subsurface as we operate these open loop systems. And I'm going to look at two types of deployment. I'm going to look at a system where we pump groundwater just to provide heating and cooling, and I'm going to compare that against systems where we store energy underground and reuse it. And if you kind of take away one message from this first part of my presentation, if you fall asleep for the next 20 minutes or so, all I want you to remember is that we can operate these systems using very similar infrastructure. We need boreholes, hydraulic pumps to pump the groundwater, heat exchangers and heat pumps, but if we store and reuse waste energy underground, we get longer term sustainability, higher heating efficiency with lower CO2 emissions and lower electricity demands, and almost free cooling, which is why I think this is a really attractive technology and why I'm particularly interested in the geological fluid mechanics of it. Okay, so how does this really work? Okay, how do we actually provide this low carbon heating and cooling? Well, let's look at kind of a system where we just pump the groundwater. These are non-abstractive systems. We don't net abstract any groundwater because we re-inject everything that we produce. So we would have an aquifer sitting underneath our building of interest and some boreholes. And when we want to provide heating, we're going to produce some groundwater. We're going to pass it through a heat exchanger and then use a heat pump to boost the temperature on the building side. And that means that we then discharge some cool water back into the aquifer after heating. And actually, if we want to provide cooling, we can switch this around. And now we can take out our groundwater, which remains at about a constant temperature, 13, 14, 15 degrees typically. And we can still pass it through the heat exchanger, but now we use the heat pump to drop the temperature to provide cooling, and we would inject some waste heat back into the aquifer. And this is, as we'll see, more efficient than using air source heat pumps very often because of the relatively constant temperature of the groundwater. And what we do in the aquifer, and we're going to see a lot more of this as we go through the presentation, is create some plumes of warm or cool water. And so this is an example of a plume of warm water that's been injected into the aquifer from these two boreholes here. And one of the things we need to understand is where that plume goes, what the fluid dynamics mean in terms of where that plume will go in the subsurface. Now, we can operate this system in a different way. Same infrastructure or very similar infrastructure. What we can do is when we want to provide heating, we can abstract groundwater and pass it through our heat exchanger and inject the cool waste. When we want to provide cooling, we switch the system around. So this time, we produce from the borehole where we injected that cool water, and we produce back the cool water that we stored there, and we can provide cooling. And in fact, if that cool water is cool enough, we can provide that cooling directly without having to use the heat pump. And as we're going to see, that makes a huge difference to the coefficient of performance, so how much extra cooling we get per unit of electricity we supply, because we don't need to run the heat pump, and that's the main consumer of electricity. We store the waste heat in the aquifer, and then when we want to provide heating, we switch it around again and produce that heat back to surface. And so that makes our coefficient of performance more efficient for heating because we supply the heat pump with some pre-warmed groundwater. And what that does then is to create now plumes at the separate boreholes And we can operate this kind of in a seasonal way. So it's a good way of shifting cooling from winter to summer and heating from summer to winter. So we can operate it in summer. We abstract from what's called the cool well at some lower temperature and provide cooling, and then we inject the waste heat and we can store it there until we need it. And in the winter, we then switch the system around, produce that nice warm water, boost the temperature with a heat pump and inject the waste cool. And we can operate this now on a seasonal basis to provide low carbon heating and cooling. And what that means in the aquifer is we get something that looks like this. The plumes grow and shrink as we inject and abstract the water. So when we provide cooling, the warm plume grows, and when we provide heating, the cool plume grows, and vice versa. And one reason I wanted to show you this is because we're going to see a lot of numerical simulations of these processes solving the equations that Fleur talked about before for Darcy flow of groundwater, advection, diffusion and dispersion of heat, and so forth. But we do this on a mesh that adapts. So we actually borrowed this from fluid dynamicists in other areas, particularly in aeronautical engineering, where they're interested in capturing shocks. We want to be able to capture these sharp temperature gradients and also gradients in salinity and contaminants and so forth. So we use an unstructured mesh that adapts dynamically in all the simulations. And it also helps us with this unstructured grid to capture very complex geometries, which you're going to see are very important in controlling where flows move in the subsurface. And this is really very unusual in the groundwater modeling community. They tend to use regular grids which remain fixed during simulations. So this is a kind of simulation we can look at where this is kind of now a 3D view looking at how those plumes would grow and shrink in the subsurface during operation of one of these aquifer thermal energy storage systems. And these look like really nice, simple cylinders. And that's true if we have a lovely homogeneous aquifer with no variability in permeability or porosity. Now, we're going to see that's not the case in most of our natural systems. So to give you an idea of some of the scale of these projects worldwide, typically you're looking at aquifers tens to hundreds of meters in depth. This is a shallow geothermal technology. We're not going to sort of 500, 800 meters depth. You need a minimum of 2 boreholes, warm well and a cool well, but you can scale up the system by drilling additional boreholes for larger power. The heating and cooling power, this is kind of megawatt to tens of megawatt scales. This would be supplying large buildings, an airport in the example shown here, or hospitals or heat networks, and you're looking at storing kind of order gigawatts to hundreds of gigawatt hours of thermal energy per year. Now, there is one place that really dominates in this technology, and that's the Netherlands. They have around 3,500 ATOS installations already operating. And one of the reasons for that is that they've been really good at promoting this technology. The other is that they have very nice homogeneous aquifers. If you look elsewhere where the aquifers are more complicated, there's a lot lower take-up. So here in the UK, just 11 ATOS systems, but not 0. We do have some deployments. And an example of one of those is in London. It's in Wandsworth. It's called the Wandsworth Riverside Quarter. And this is an ATOS system that's supplying a mixture of residential and commercial units in this modern development. It has 8 boreholes. It has 4 cool boreholes and 4 warm boreholes. And this has been operating now for around about 8 years, delivering up to sort of 600 to 700 megawatt hours thermal a year of heating and cooling, and saving sort of 200 to 250 tons of CO2 annually. And we're going to look a little bit more at this system as we go through the presentation. So one of the things I'm going to emphasize is that we really need to have holistic solutions for heating and cooling, and they tend to be looked at as separate problems. So we look at heating, we think about supplying heating with boilers and so forth if we're happy to burn gas, or we might think about having dedicated ground source or air source systems for heating. If we're going to operate groundwater systems, though, what's really very useful is to have what's called energy balance. Okay? That would mean that we extract and inject equal amounts of heat and cool into the subsurface. Because as Fleur pointed out, if we're very unbalanced and we inject lots of waste heat, or lots of waste cool, we need natural processes to take that away from the system. Otherwise, we get a plume that grows bigger and bigger and bigger, and it risks breaking through and contaminating our abstraction wells. And the other issue, as Fleur pointed out, is if we just install lots of systems for heating or lots of systems for cooling, then we can start to impose big changes, significant changes in the overall aquifer temperature, which can start to affect our system efficiency and also the efficiency of systems installed by our neighbours. So I'm going to be kind of pushing the idea today that we want to look at systems where we integrate heating and cooling, and so we can use the aquifer to provide both in a balanced way, which means we have a really long-term, sustainable, low-carbon heating and cooling technology. And that fits in with the fact that we do see a significant increase in demand for cooling. Heating is not the only problem that we face. So just to give you an example of what can happen if a system is very imbalanced, this is a system in Liverpool that was operating for a hospital, and in fact the cooling demand was much bigger than the heating demand, so lots of waste heat has been injected back into the aquifer, which has caused a hot plume to grow bigger and bigger and bigger. And so if you look at the temperature of the boreholes as a function of time, this is what we're injecting. So we're injecting heat, a bit of cool, heat, and a bit of cool. So you can see that we're unbalanced and injecting and rejecting more heat back into the aquifer. This is the temperature of the production wells. So this system is providing essentially a lot of cooling, but the problem we have now is the production temperature is starting to increase. So we're now making our heat pump do more and more work because it's taking warmer and warmer water in and having to drop its temperature. This is a system where we've had thermal breakthrough, and it reduces the efficiency with which we can provide cooling or heating. So you ask, we live in the UK, right? Is balance even possible? Surely heating is always going to exceed cooling. We can look at the system in Wandsworth and also Dutch comparators with a very similar climate to the UK. And in actual fact, if you look at, this is the injected warm, the injected cool, and so if you lie on this 1-1 gradient here, you're a nicely balanced system. In fact, most Dutch systems are balanced, and the Wandsworth Riverside Quarter system is also nicely balanced. If you provide people with cooling, they tend to use it. And one of the reasons why we underestimate how historically provided it. So if I had £1 for every time I've talked to a building services engineer and said, what's your cooling demand? And they said, we haven't got any. That's not true. They haven't historically provided any, but you ask the inhabitants of the buildings whether they'd like cooling, and the answer is normally yes. We would very much like it in summer. So what we're looking to do is develop systems where we can provide that balanced heating and cooling. And in fact, if you look across the systems in the UK, they in fact have pretty much equal, or in fact cooling demands that exceed the heating demands. So this is a list of different ATIS systems, and this is the heating and cooling load, and you can see in fact the cooling and heating peak loads are in fact pretty similar, or in fact cooling even exceeds heating. So one of the things we've seen historically with incentives for low carbon heating systems is that they have really prioritized heating over cooling, so they penalize cooling if it's offered. And in fact, they've also incentivized just the production of heat and not the storage and reuse of heat. And that would be something we really need to drive change in to see these systems being properly incentivized. So, not really said very much about fluid dynamics so far. One of the things we might be interested in here, and we are interested in, is in fact how efficient is the thermal storage? How much of the stored energy do we get back? So we can look at the data from the Wandsworth system, and we can define this thermal recovery factor, which is essentially the fraction of what we store that comes back to surface, and it's actually rather small for the Wandsworth system. It's much higher in Dutch systems. They can get 60 to 90% of the stored heat or cool back. So we might want to ask why that is. So, when we inject this warm and cool water in a nice homogeneous aquifer, you store in my little animation, you get these nice cylindrical plumes that grow and shrink. And it's very easy to characterize the maximum size of that plume, the maximum radius of that plume in terms of what's called the thermal radius. And so one of the things the Dutch would say is that, well, you need to put your wells far enough apart to make sure that you're not within that thermal radius. If you're too close, you know your heat's going to meet your cool well, your cool is going to meet your warm well. If you're a bit further apart but still too close, those plumes will interact with each other. If you put the wells far enough apart, you get nice separate plumes. So, the aquifer that the Wandsworth system exploits is the chalk aquifer in London. And that's a very heterogeneous aquifer. So one of the ways we can tell that is by looking inflow to boreholes when we pump them. So the chalk actually sits below about 80 meters of London clay. That's an impermeable layer. It's an aquitard that confines the chalk. We drill the boreholes into there, and then when we can pump the well and look at where the flow is coming into the borehole, and in a nice homogeneous aquifer, the flow just increases linearly from the base of the well to the top. What we see in the chalk is very different. We get almost no inflow in this borehole and then lots and lots of inflow at the top. In some boreholes it's a bit different. We see evidence of no flow and then lots of flow coming in at a rather deeper horizon like this. And these wells are only sort of tens of meters apart, so there's clearly a lot of lateral variability in these flow horizons, which I've called karst and fracture, and I'll explain that in a minute. And in fact, if we look at other boreholes around London, so this is in fact inflow from a borehole at Imperial, we see a very similar pattern of very focused inflow, and it's kind of well known in conceptual models of groundwater flow in the chalk. So why do we get all this flow at the top of the chalk? Well, this is when dealing with kind of underground systems becomes challenging, because unlike most fluid dynamical systems, we can't directly image them. They're underground. This is 80 meters of London clay we've got to get through before we even see the aquifer that we're dealing with. So we have to try and understand what's happening from relatively sparse data. So one of the things we can do is look in the boreholes. So this is a borehole video camera down well at Hammersmith, which is operated by, it's part of the Imperial Healthcare Trust. And this is kind of looking down the borehole. And if you look at the side of the borehole, at where we saw that inflow, we actually see we have little caves. These are kind of the scale of tens of centimeters. It's a karst system where the chalk has been essentially dissolved out by groundwater flow. And that gives us some very high permeability for flow. The thing we don't get from this is, well, how does that vary away from the borehole? And that's very difficult for us to characterize, but we can go and look at places where we see the rocks at the surface. So these would be outcrop analogues. So we can go and look at the chalk a little bit outside London. And what we can see here is, in fact, this is a karst horizon. And we can trace the base of the karst. This would be a kind of a dissolution pipe. And we see that it's very, very irregular. So we've got lots of variability in the thickness of this karst horizon. And we can also go and look at other features that might impact on flow. So we can look at fractures. So these fractures are going to be very permeable. And in fact, the chalk rock itself, it's a bit like the situation that Fleur talked about here. The chalk rock is very low permeability. It's tiny grains. So most of the flow here is going to occur in fractures or in this karst horizon. And in fact, what we see here is the fractures tend to be pretty high angle. And we also have these layers called marls, which are kind of very soft, and they tend to truncate the fractures which only occur in the brittle rocks, in the brittle chalk rocks. So then we can kind of take this sort of information and start to build some conceptual models of what we think the geology is doing in the chalk aquifer. So we've got here, these are all 3D models, these are some 2D sections through them. So this is our karst horizon with this kind of undulating base that we saw in the outcrop. We've got these fractures here. Sometimes we might say they're truncated by marls. We've also got evidence in London that we have some faults that may offset some of the layers. We can put these faults in here that would offset the marl layers, for example. And then we can run these through some numerical simulators to see what impact it has on plume development. So this is one example of a simulation here. So now you can see that the plumes are really kind of exploiting that karst near the top of this is basically the London clay. We can see the karst horizon shown here, and this is the temperature field as we provide heating and cooling to the Wandsworth system. But we also, we see some flow coming into a fracture. That's dipping towards us, so it's hard to see in this 2D plane. But I have kind of a close-up of the plume around one of these systems, and the video's a bit slow, so I'm going to kind of drag it. But what we can see here is this is the plume spreading out and intersecting with an almost vertical fracture. So you get this kind of flip. It kind of flips from being this flat feature here, that's horizontal, to being almost vertical. It starts to meet the cool well very early on, so we get thermal breakthrough. And then we see the cool plume going almost vertically there in one of those high angle fractures. And so it's got a completely different and much more complicated geometry than those simple cylinders that I showed you in a nice homogeneous aquifer. So what we're seeing here is that we really have much, much more complicated flow and plume geometries in these heterogeneous aquifers than we would see in the Dutch equivalents. And if you compare an ensemble of predictions, so we run lots and lots of forward models because we have uncertainty in the aquifer description, and we kind of bracket that simulated behavior it actually looks pretty similar to what we see in Wandsworth. And so we can argue here that that low thermal recovery is due to thermal interference caused by the very complicated flow paths. So for me, you know, the geological fluid mechanics here really comes around predicting the plume migration and the associated heat transport in the subsurface, so we can really understand and predict how the system's going to behave. And in fact, engineer and design systems that can be more efficient than if we just assume a homogeneous aquifer. We want to avoid thermal interference and thermal breakthrough and minimize those thermal losses, but it's still very common to see lots of models where they have those lovely cylindrical plumes that look very, very simple. And that's what we need to move away from. So, low thermal recovery. Does that mean that the system's not worth anything? Do we get no low carbon energy production? Well, the answer is no, okay? It's still a useful system. What we can do is we can take the energy that would be produced from one of these systems. It's basically the production, we can look at the temperature drop across the heat exchanger and the flow rate and the heat capacity, and we can use that to calculate the heat that's going to be produced or the cool that's going to be produced. We can actually kind of break that down into two contributions. One of them is the contribution you would get just from an open loop system that's producing groundwater at constant temperature, and then the additional contribution you get from storage, and that's multiplied by this thermal recovery factor. So what you see is even if you end up with a thermal recovery factor of 0, you're just going back to a standard open loop system. You still get low carbon heating and cooling, you just don't get the benefits of storage anymore. So 0 thermal recovery takes you from an H system to a classical open loop ground source system. And we've done a whole bunch of modeling to look at where, you know, which might be optimal in what situation. So this is basically energy produced from an ATIS system versus a standard open loop system. And we always lie above the gradient of 1. You always get more out of an ATIS system because on average you don't have 0 thermal recovery. And we've also looked at the energy density. So that's how much energy you could get per unit area of ground that you need for the system. That's really important in cities because we have lots of demand and very small area to supply that. And you also get significantly higher energy density from implementing ATIS systems. One of the things that we could also look at is groundwater flow. So Fleur talked about that as being the enemy of storage, and I agree with her, it is, right? So what we're looking at here is different ATIS systems with different groundwater flow rates. No groundwater flow and then increasing groundwater flow. And you can see that that does take the heat away from the ATIS systems. If you have groundwater flow moving those plumes, you're going to get less of that back. But you have to get to relatively high flow rates before that really becomes a pain. And in fact, if you compare an open loop system and an ATIS system, all that happens is that the groundwater flow takes you back to the open loop kind of baseline. So groundwater flow does reduce recovery efficiency, but you're still not doing worse than a groundwater heating and cooling system. So what we could do now is have a look at, you know, how they match up in terms of electricity consumption and CO2 emissions. And really the key here is electricity consumption because that drives the CO2 emissions for the given energy mix. And what you can see is, of course, if we just use direct electricity, our coefficient of performance is 1 unit of electricity for 1 unit of heating or cooling. Air source heat pumps, we need a higher electricity demand, they have a lower coefficient of performance. ATIS always comes out best for heating, and it's very, very low for cooling because we can often deliver cooling without having to use the heat pump. And that then translates straight through into CO2 emissions for various predictions for the energy mix going into the future. But the key point here is that ATIS delivers heating and cooling with lower electricity demand, which can often be very useful on a local scale. Your DNO might not be able to supply the electricity you want. You need to be as efficient as possible, and lower CO2 emissions because you provide warm water to the heat pump for heating and cool water which might be cool enough already to provide cooling. And the last thing I want to say, so Fleur talked about what a contribution, shallow geothermal could make to heating in Leeds. We kind of looked at a national scale assessment of what contribution ATIS could make. We do see a nice alignment of aquifers shown here in green and major population centres, including Leeds, and heating and cooling demand. And what we see is that we've done a probabilistic analysis for this, and ATIS, if widely deployed, could supply around 60% of the UK's heating demand and around 80% of its current cooling demand. It could provide a lot more cooling, but we just don't have that much demand at the moment. So I think my point here would be that, and we've had a lot of in the fluid dynamical context, a lot of input to this from understanding plume migration is that ATIS systems offer this long-term sustainability through balanced operation, very little net change in aquifer temperature, higher heating efficiency, almost free cooling, and it could make a really big contribution to the UK energy mix. So what we're trying to do now is to work that through into policy and into regulation. We think you should always consider an ATIS system ahead of a groundwater heating and cooling system. But the geological fluid mechanics here is all around understanding what's happening in the subsurface. And I would say the biggest challenge to the uptake of the technology at the moment in the UK is that no one has ever heard of it. So I should have probably got you to put your hands up at the beginning to say how many people have ever heard of ATIS in this room. Let's do that now. Before I walked in, or before you listened to my talk, how many of you had ever heard of ATIS? Well, I know you have, because I've worked with you, right? So that's cheating, you can ignore them. Okay, I can see your hand over there. Great, so there is a little bit of awareness. Okay, how am I doing for time? I've got one other thing I'd like to talk about. Lest you think that geological fluid mechanics and the energy transition is only around heating and cooling, I'd like to talk about something completely different for the last 15 minutes or so, if I have time, which is what role fluid mechanics might play in finding critical metals. So the challenge here is copper. We know that copper demand is forecast to increase a lot. That's largely driven by the electrification of the economy, and we know that supply from existing and announced projects is only going to cover around 70% of demand by 2040. So a big copper gap is on the way. Why is geological fluid mechanics relevant to this? Well, it turns out that copper is transported in and precipitated from natural saline brines. When those brines encounter a change from oxidizing to reducing conditions, that triggers mineralization, and we get minerals like chalcopyrite being precipitated. We can have these fluids occurring in magmatic systems. We can also see them in sedimentary basins. And the fluid dynamics largely controls where those deposits occur. So I'm going to talk a bit about sediment-hosted copper and fluid dynamics. So a sedimentary basin is basically when the Earth's crust opens, it makes space, and processes like the movement of rivers and seas deposit sediments in that space. And so you start to occupy, this is basement rock, this is not sediments, this is where we're opening to make space, and that space here has been filled by sediments of various types. We can get salt in these basins, which can provide a source of very saline brine. We can have various different rock types, in fact the kind of rocks that we would exploit for shallow geothermal, so we might have a little tiny system. The scale of this is very large, this might be tens to hundreds of kilometers laterally, and hundreds of meters to kilometers vertically. And there's an argument that says that copper is, well, we know that copper is found in these basins. The Central Africa Copper Belt is a sedimentary hosted copper system. We know that copper is found in these basins. The question is, how does it get where we find it? And there's an argument, a lot of that is driven by flow, and that flow either has to bring copper into the basin from outside, so we have some kind of extra basinal copper source, or maybe the copper was already in the basin, it was redistributed and precipitated by flow to give us some ore deposits. And the base of many of these sediment, of these basins is often full of what are called red beds, continental red beds. So red sandstones where the grains are all red because they've got iron oxide coatings. And one of the things we know is that groundwater can leach those iron oxide coatings and can bleach the sands back to being kind of white or grey again. And this, in fact, is an example from the UK where you can see these bleached horizons and these otherwise red sandstones. And those iron oxide coatings contain lots of metals. Some of them we want and some of them are nasty and poisonous. So we've done some experimental work to look at how efficiently we could leach off these iron oxide coatings. So this is what happens before we leach, and then we leave the system leaching away for some time, and we actually see that we can bleach these sands back to being pale. And when we do that, lo and behold, we find that we do get copper. So we look at iron as a proxy for leaching, because these are mainly iron oxide coatings. And what we see is as we leach off more iron, so we produce more copper, not in enormous concentrations, but still, we get some copper off these red beds. And we have a relatively positive correlation, but a lot of variability around that. And these samples span barren basins with no known mineralization through to basins with lots of copper in them. So then we come on to doing some numerical modeling. We've built some basin scale models. This has gone from the tens of meter scale I showed you before to the kilometer scale laterally and vertically. And we have a model of a sort of a classical sedimentary basin fill with some big faults that also act as flow paths. And we actually look at two stages. These basins kind of fill through time. So we looked at two different steps in the basin evolution. And we've got these kind of questions we want to try and get from the fluid dynamical modeling. So what we get is some models that look like this. And now look at the time scales. We're now simulating on millions of years, not months to years. So really long time scales and really big length scales. What we're seeing is lots and lots of convection. So this is looking at those big faults. And we're seeing that we get flow moving across those faults. And this is looking into the red bed deposits that we see where we might be leaching the copper. Now, what we see really is two different styles of convection. So I'm going to kind of take you and just show you those. When we model in here salt water moving into the basin, and when we have lots of salt water moving, and that really dominates the convective patterns. So we actually get some downwelling limbs in the faults and some upwelling portions here, and we see a little upwelling portion there. And then once that salt mixes in, we actually see a temperature-driven convection that dominates. That's much simpler. Really just downflow in this fault and upflow in that fault. But what we see is this convection is very complicated, it's three-dimensional, and it occurs at multiple length scales, and it changes through time. It's very dynamic. But what we don't see is any copper. No copper gets leached or moved. Everything is too cool and not salty enough. So then we go to the later stage portion of the system. We bury things under some more sediments, and we look at what happens then. And then we do start to see mineralization. So what we have here is, in fact, an organic-rich layer which acts as a redox boundary. So the flow has to bring the copper to this redox change, and then it precipitates because it goes from an oxidizing to a reducing condition. And what we're seeing here is, in fact, copper being deposited. It's being leached out of the red beds, but also out of the basement rocks. It's moving through this convection. And what we see is we get copper being precipitated that's associated with portions of that fault where there's upwelling, and also patchy bits of copper where we get little local convection cells that take the copper directly from the red beds up to this redox boundary that sits right above that. And we see this takes a long time, okay? This is not a single pass. This has been argued about in the geological literature for a long time. It's not a single pass of enriched copper brine. We have to have lots of cycles of convection to leach some more copper and move it and precipitate it. And that's starting to address some challenges that we've had in the literature about how this copper moves that have been discussed but never really modeled from a fluid dynamical sense. So the key thing here is we get these different large and small scale groundwater convection cells, and they're controlling where we see the precipitation of copper. We see some associated with faults, and we see some associated with little local convection cells. So the key thing here, and this is really the first time it's been modeled at this scale, is that it's groundwater convection that's driving these processes that controls copper mineralization. It redistributes heat, it increases the source rock temperature, so leaching happens more effectively, it gets the saline brines there, and it gets the copper from the source rocks to where it's deposited. But these convection patterns are really complicated. People have tended to always just think of them as being simple, standard, kind of stable cells. They're not. They're really variable and multi-scale. But it's where those cells are bringing copper-rich brine to the redox boundary, that's where we see copper being precipitated. And that kind of insight can drive models for copper exploration. So if I have 2 minutes left, is that okay? Great. The last thing I want to talk about is whether we can also use fluid dynamics to extract critical metals with much lower environmental impact. This is a typical copper mine. It's enormous, a massive hole in the ground, and we waste huge amounts of energy blasting the rock, moving it around, putting it through separation processes which use lots and lots of water and energy to get the copper minerals out. So this has a massive impact on local populations. Now, I have never in a talk before used an oil reservoir as an example of potentially good environmental practice, but we were looking at the Witch Farm oil field. Now, that's below Poole Harbour. This is an aerial photograph. There's actually 1 billion barrels of oil under here. About 500 million has been produced since 1979. There's almost no surface evidence of it. You can just about make out little patches there's some drilling platform, there's some kind of drill well sites kind of around here. And I've actually been kind of giving a talk to students, and someone's got out the car and said, I've lived here all my life. I had no idea there was an oil reservoir here. So I think if we could do something like this for mining, that would be really exciting. Imagine having a copper mine next to you and you have no idea it's there. That was kind of what motivated us to think about whether we could do copper mining very differently. So, lots of volcanoes emit lots of metals, okay? And we know that more of those metals remain trapped in very saline brines just a few kilometers beneath the edifice. So what we're doing at the moment is some research to identify candidate volcanoes that will have these copper-rich brines using fluid dynamical modeling, coupled with kind of imaging what's in the subsurface, so looking for places where we see saline brine. These brines could be directly mined for metals using existing geothermal technology, and the brines are hot, so they could also be used to supply geothermal energy. So the question is, can geological fluid mechanics deliver us a self-powered copper mine with much lower environmental impact? That's a little look to the future. That's all I had to say to you today. Thank you very much.
Thank you, Matt, for a super talk. Can we take some questions?
Yeah, thanks very much. That was great. Just a couple of questions. The first one about the A-test, is it A-test thing? How does the sort of contamination risk for that compare to some of the deeper water examples of geothermal? Because that can be a bit of a problem, can't it?
So typically we're exploiting with ATIS systems aquifers that are potable, that have kind of, fresh water. And so the main risk perceived, when you put these systems in, is that you're changing the temperature, and heat is a contaminant in the subsurface. So you do need to be aware of that, and one of the permitting requirements will be to look at where that heat is going to go, how far it will move away from your system. In some aquifers, it is true that you may have some portions of those which have got some contaminants in them. So we've actually looked at this. We looked at a very common contaminant is salt. So as you drill deeper, you can move from the freshwater portion of the aquifer into the saltwater portion of the aquifer. And I didn't have time to sort of show this, but we've looked at what happens if you pull some of that salt water into your well and then redistribute it around the ATIS system. And it turns out that the effect remains still very localized to your ATIS system. And even with groundwater flow, it's transported relatively slowly. So you can design exclusion zones around the ATIS system, which would mean that you would not be at risk of contaminating other users of the groundwater resource. And in fact, in places like the Netherlands, where they do install a lot of ATIS systems, it's fairly standard to have exclusion zones around freshwater production wells to make sure that you're not risking contaminating those, and I think we should have something similar that we would implement here.
Yeah, great talk, thanks. On the copper, just interesting, so I haven't seen this before, so you straighten me out if I get this wrong. But so it's that redox horizon that's crucial. So you said, I'm just thinking Alderley Edge. I don't know if you've been, the copper mines.
Copper mines, in Alderley Edge.
Along it, but a lot of it's along the faults. There's some flats.
Yeah.
It's very fault. So if the faulting was generating an oxidation to redox environment locally, then the mineralization would stick around the faults.
Absolutely, and that would be a very localized redistribution of the copper pretty much within the red beds. And you're right, so what you would then need would be some local redox or change in redox conditions that would cause that copper to precipitate. Now, the reason why it's often associated with organic rich layers to provide you with that redox change is just observational, right? That's where we see the copper mineralization occurring in most of the main mineralized, kind of basins of the world. But it has been argued that there are other reasons why that would happen, and one of them, for example, is petroleum migration. So there's been an argument made that that can also change the redox state, and there could be an association between petroleum being locally present and copper mineralization being driven by that change in redox. So it's perfectly reasonable that it's not always driven by the presence of some kind of organic rich layer. There could be other drivers for that redox change. The point would be it's fluid mechanics.
I like the idea with the copper being cannibalized essentially within it.
Yeah.
There's the scope, not in every case necessarily, but some of the authors for that work that suggest that it's really exotic sources of it, but actually a lot of it could be local.
Yes, absolutely. So you've got local source from an intrabasinal source from the red beds that's being redistributed by convective groundwater flow and then being precipitated. And you're looking for those controls on flow. So it's all about faults and maybe local flow paths like fractures where you would see that copper being mineralized.
Thanks. Can I take us back to the A-test? As I understood it, the cracks, the geometry of the cracks in the chalk are critical to the flow. But you also made the point you've got 60 or 70 meters of clay between the surface. So how can you have confidence in your CFD or your flow modeling when perhaps it's going to be quite difficult to model the geometry? Or what's the sensitivities involved in that?
You're absolutely right. So, I mean, what we see, an outcrop, I mean, Dave would have a lot to say about this as well, I know, and probably other people in the audience. The structurally controlled aspects of heterogeneity are much more difficult for us because they can depend a lot more on the local stress state and the overburden and so forth. Whereas we kind of feel that, so, you know, with the matrix control variability, that's probably less sensitive to those conditions. So what we did with the modelling in the chalk is that it was, we observed the fact that we see these high angle fractures in the outcrops at the quarry. We also used the fact that very often in these rocks you get these conjugate fractures that form, and we basically used a combination of observations and kind of conceptual ideas around what we think these fractures would look like to develop a range of different scenarios. So I'd say they're scenarios that are informed by observations of the outcrops, but they're not solely based on those observations of the outcrops.
Thanks.
So we actually ran a whole bunch of scenarios then, which is why I would have had a massive cloud of data on that plot, and I just bracketed it with the dashed lines.
Matt, excellent, really lovely talk. I wanted to understand, you teased us with 2 bullet points that you didn't cover. Yep. Did you want to tell us something? What's your message? Because both of these are highly important topics that face our country as well as the world, I suppose, over time. What was the message you were going to get there if you didn't have the time?
Well, I guess I was thinking about this from a fluid dynamical perspective. So from a fluid dynamical perspective, you know, deep geothermal and CO2 storage, they're really interesting because then you move into multi-phase flow in the pore space, okay? Whereas everything I talked about today, we just had groundwater flowing of variable salinity and temperature. And once you go into multi-phase flow in the subsurface, the physics and the fluid dynamics become a lot more challenging, okay? And you could even start to develop shocks, for example, which you need to try and resolve in your numerical modeling. You're starting to get really into pore scale processes around how the fluids are arranged at the pore scale, which then impacts a lot on how they move at the macro scale. You're looking for CO2 at processes of dissolution into the brine and mineralization, which can cause trapping. So the fluid dynamics become really exciting for CO2 storage. Why didn't I talk about that today? We are looking at CO2 storage at Imperial. I think we should stop recording because I'm going to say something quite controversial. I don't think we're ever going to do it at scale. I like working in geothermal because I think we're going to do it. Okay, I think it produces something useful. Okay, so we can see the value from that and we can make arguments about the cost, but it can be used to decarbonize heating and cooling. The worry I have with CO2 storage is that it's a political decision that's entirely cost-driven. And my worry is that we're going to write more papers about CO2 storage than tons of CO2 we actually store underground. And so it's kind of pushed me into working in geothermal, even though the fluid dynamics of CO2 storage.
So just a comment on what you were saying about CO2 sequestration. Just firstly, I did my design project on that at my undergraduate 20 years ago, and I'm not sure the dials move that much forward.
Yeah.
But,
it's like fusion. We're going to do it in 20 years' time.
That's another topic. I do some work in fusion. I agree with you.
That's a great track record.
But I just got a practical question on the heat pump. When you're talking about cooling and the importance of it, and you're saying sometimes you don't need the actual heat pump bit. So, because some of it is my sort of misunderstanding of how they work. They have some sort of radiator systems for the heat pump sort of passes, or my understanding of air heat pumps anyway. And so the heat is delivered through, I guess, a type of liquid radiator. How's the cooling delivered in say, that Wandsworth example?
So it's all air handled in Wandsworth. So it's like having an air conditioning system in your flat. But rather than being powered by a compressor on the wall with a vent outlet, it's being taken directly from a building scale redistribution of heat and cool. And in fact, the Wandsworth system, there's lots of things about that are very neat. I mean, in fact, it redistributes heat and cool internally within the building. This is not my area of expertise in fluid dynamics. There'll be people in here who know this much better than I do. But they actually use passive heating and cooling before they even start to call on the ATIS system. And so, in fact, the ATIS system has operated a lot less than I think they expected it to, because it's been quite a successful redistribution of heat and cool around the building. But that's mostly handled by air. They don't have kind of traditional radiators. And I think that's, again, straying outside my area, but that is one of the challenges to retrofit these systems into old buildings, is that you can't use radiators for cooling because you get condensation on them and so on and so forth. You have to have a different method of delivering the cooling, whether that's in the ceiling or via air or something like that.
So what you're saying, if I get it, the removal of heat in the summer is almost as advantageous or generally good enough rather than delivering coolness. It's the
so the top floor flats, they tend to be a net contributor of heat into the system that gets redistributed down into the lower floor flats, which are more in shade, and that internal redistribution already provides cool comes up and heat goes down through the internal redistribution system. That's already providing heating and cooling before you even begin to take anything out of the ATIS systems. The ATIS system is like a net contributor. When it's needed, when the internal redistribution can't meet the heat or cool demand, then the ATIS system kicks in to meet that missing supply.
Okay, great.
But there's a kind of a social equity issue here, which also I didn't. But the Wandsworth development, and nearly all the development of ATES in London are luxury apartments. And if you go on the website and look at it, they sell this cooling as it's a big marketing thing they use. And I think that it's sad that we are deploying these technologies at the moment primarily to luxury apartments when it's people who live in who are much more disadvantaged socioeconomically who are really suffering from overhot. So we're really trying to persuade housing associations and so forth that they should be putting these kinds of systems in as well to make their properties livable in the summer as well as the winter.
Okay, could I just ask, the saline flows you were simulating, I understand you're the first person to do it. How are you going to sense check what you're predicting if it's over the scale of 1 million years?
Absolutely. So I think that this is where it's the level of prediction you expect to make. So when we're trying to simulate an ATIS system, I think it's fair to say that particularly if we're looking at one that's operating, we want to get as close as possible to the real physical operation of that system as possible. And if you're trying to predict, when you install a new ATIS system, you really want to get some good sense of the heat it's going to produce, the cool it's going to produce, and where the plumes go. So there's a responsibility there in the modelling to be as close to reality as possible. When we're doing this kind of modelling, I don't think that any basin will ever do exactly what we think it's going to do based on the fluid dynamical predictions. But what we're looking at here is to inform conceptual models that are often used by economic geologists to make predictions around where they think copper is going to be found. Now, convection, for example, has been very frequently invoked in cartoon representations of sedimentary basins as a mechanism to move copper around. But it's nearly always very simplistic. You've got some big loops that do this. And I think what we were trying to get across here is that, in fact, the convective patterns are going to be much more complicated than that, much more time variant than that, much more multi-scale than that, and that should be informing the way that people think about these systems. So I work a lot with earth scientists, and because earth science systems are very complicated, there's a lot of conceptual models out there that people kind of draw, cartoons that they draw. And I think it's our responsibility as people who understand, the fluid dynamics and the physics and so forth to sense check those and say, actually, that's not a bad conceptual model. I can see there's a physical support for that. Or actually, that's much too simple, or it's wrong, the scales are all wrong, your rally numbers are all wrong, or whatever it is. This is how I think it's going to behave in a more realistic way. Will a sedimentary basin actually do what I've predicted? Probably not. But I think we're just trying to inform the way that people think about these systems in a conceptual way.
Any more questions? Well, in that case, let's thank Matt again. I'm afraid you don't quite get to go yet, because Kath is here.
Okay, yeah, thank you, Chris. So just to finish up today, I'd say a big thank you to everybody who came. And you'll have all noticed the posters outside. So we have had a little bit of a poster competition for those who put posters in. I'm afraid I haven't got anything to actually give you now, but you talk to Chris. He'll sort of sort you out at some point. We've got 2 prizes. So our runner-up prize, if he's here, Chris Jackson. I'll shake your hand and pretend to give you something. So, but thank you, well done, excellent. We got a photo from Karen. There we go. And our first prize is to Katerina Kairu, if she's here. Very well done. So well done to both Chris and Katerina, and thank you to... There is money involved, so you will get something at some point. But yes, thank you to all the people who put the time and effort to put posters together and for talking about them to people. And from me as well, thank you very much to everybody for coming and for 3 fantastic talks this evening.
Done the final thanks for me. So thank you, everyone, and thanks to our speakers, and thanks to the house team as well.